few lectures and in the lectures during the course, we will derive some partial differential equations that are used in mathematical physics as models of processes of natural phenomena. And a popular approach towards the derivation of these models is to use fundamental principles such as conservation laws, for instance, conservation of mass, or conservation of energy, conservation of momentum. And in the optimal case, we are able to start with the fundamental laws and then average them to obtain simpler models. And in this video, I will remind some material from calculus that students typically forget and ask to be reminded. So we will start with this lemma, and first we will formulate it in one-dimensional case because we are able to draw a nice picture. So let function f of x be a continuous function on some interval ab of a real line, satisfying the condition that integral on any subinterval cd, subinterval of ab, equals 0, and then f of x is identically 0. And so I want to stress that two words are important here. First, that function f of x is continuous. We will be using this property. And second, that it's not only integral along the interval ab equals 0, but on any subinterval, because if it's just integral along the entire interval ab is 0, that will not be true. But the word that on any subinterval integral is 0, then f is identically 0. And proof by contradiction. So we assume that exists a point x naught such that f of x naught is not 0. And in this case, what? It's either greater than 0 or less than 0. And without loss of generality, we assume that this happens. So f of at this point x naught is greater than 0. So if it's greater than 0 and our function is continuous, then by continuity exists a small interval a sub 0, b sub 0, and a positive number epsilon such that f of x greater than epsilon greater than 0 for any x from this subinterval. So I made the picture here, right? So it's my x-axis, and we have this point x sub 0 with some value f of x sub 0, which is positive, and then we have epsilon somewhere here, and we look at this small subinterval from a naught to b naught, and then we can write that if we integrate our function along this interval from a naught to b naught, this area obviously under the blue curve is greater than area under the this pink curve. So this integral greater than this integral, and the second integral we can compute. It would be epsilon times b sub 0 minus a sub 0, and this epsilon is positive. This is also a positive number, so this would be greater than 0, right? So this is not 0, so we obtain a contradiction. So this finishes the proof. And in the next moment, I will discuss a modification where instead of x, which is just a number, I will consider a vector in Rn. Everything will be basically the same, but I thought it would be nice to have this picture. Okay, so now let's discuss n-dimensional case of our lemmas. So suppose we have function f of x. Now x would be a vector in Rn. So function of n variables, and let f be continuous and defined in some domain omega in Rn. Omega could be the entire Rn as well here. And satisfying the condition that integral for any domain in omega, any subdomain in omega, integral of f equals 0. Then function f of x is identically 0 everywhere in omega. And proof again the same by contradiction. We assume that exists point x sub 0 such that f at this point is not equal 0. And again, for definiteness, assume that it's positive, right? So we can also assume that its negative proof will be the same. So value of this function is greater than 0 at point x sub 0, and since function f is continuous, exists domain d sub 0 that surrounds, that includes point x sub 0, maybe very small domain, small neighborhood of point x sub 0, such and a positive number epsilon, such that f of x greater than epsilon greater than 0 for all x's in this domain d sub 0. And then we can write that integral of f of x over domain d sub 0 is greater than integral of epsilon over this domain d sub 0. The last integral equals epsilon times volume of domain d sub 0, and epsilon is positive, volume is positive, so everything is greater than 0, and it contradicts the Lemma's assumptions because we got that the integral is positive, integral over d sub 0 is positive, but in this lemma we stated that integral over every domain d, including d sub 0, must be 0. And this finishes the proof. In the derivation of some models, we use the notion of a flux as well as some other theorems of vector calculus. So let's review some notions of vector calculus. And first, let's recall what we call a parametrized surface, right? So in calculus, we were talking about a surface as a graph of a function, but we know that if we're talking about more general surfaces, we cannot think of them as graph of a function. For instance, if we have some kind of folded sheet, or if we have a torus, this is not a function. So in this case, we need to talk about parametrized surfaces. So a parameterization of a surface is a function phi that is defined on some domain D in R2, and its image is in R3, and the surface corresponding to the function phi is its image S equals phi of D, and so we can write phi of u and v, our parameters, equals x of uv, y of uv, and z of uv. And if phi is differentiable on, for instance, C1, then we call S a differentiable of C1. And now I want to talk about tangent vector to parametrized surfaces, but maybe first let's look at the picture that also illustrates the definition. So somewhere here in R2 we have domain D, and so we have two variables u and v, two of our parameters, and then function phi is defined on this domain D, and we have this parametrized surface. Then if we want to talk about tangent vectors, right, to the surface, so let's assume that phi is differentiable at some point u naught v naught, so here, and let's fix, for instance, first let's fix u. So let's fix u equals to constant, and we call this constant u sub 0, right? So when we talk about this, so then we have this line, and its image will be this curve. So, and this is a parametrized curve with parameter. So if u is fixed, so the only variable that changes is v. So it's parametrized curve, and we can find the tangent vectors to this curve. So then we think at this point u naught v naught at this point, right? So this is the curve. So then tv is d phi dv. So we have to differentiate each coordinates x, y, and z with respect to v and evaluate it at point u naught v naught. And similarly, we can define the other tangent vector. So similarly, we can introduce the other tangent vector. So if we fixed v, so now v is constant. So when we move along this line, we have only parameter u changing, and then the tangent vector tu can be defined as d phi du. So we differentiate every variable x, y, and z with respect to u and evaluate at point u naught v naught. And then we can define a normal vector to our surface S at this point as a cross product of tu tv. And if this normal vector is not non-zero, then the surface is called regular or smooth at this point. Right, so then here we can talk about a normal, and we also, in that case, if we have normal, we can define the tangent plane as a dot product of these two vectors, and vector n is evaluated at point u naught v naught. And we will be talking about oriented surfaces when we will be computing fluxes. So we assume that our surface has two sides. One of them we will be calling outside, the other inside. So outside positive, inside negative. So we can see it here, right? So we can, at this point, we can draw a small tangent plane, and then we can think of actually two normals, n1 and n2, right? Depending on which side at which side we look. So mostly we will be talking about outward normal. And so you might ask, what are surfaces that are not oriented? For instance, Möbius strip. And also we can talk about oriented curves. So when we're talking about a curve, it's a parametrized curve, it's a mapping, right? So we have some parameter t curve, so we assume that curve has a direction. And we can talk about different parameterization, and some parameterizations are preserving orientation and nodes. Just to remind you of the notions. And when we're talking about loops, we also can think of orientation. It will be important in integrals. So typically positive orientation, it's one if this is your domain, when your domain is kind of inside. So we can talk about oriented curves as well as oriented surfaces. Okay, now let's recall what line integrals are. So suppose we have a parametrized curve C, right? So we have parameter t running along this segment from A to B, and C is a parametrized curve with parameter t. So, and suppose that we have a vector field F, so it means that we're talking about some domain, and F vector field, it means at each point we have a vector. It could have any nature, any physical, it could be electric field, velocity field. And if we look at the integral, so the meaning of this integral is work done by vector field F, and if we need to compute this work, then we can use parameterization. It will be integral from A to B, f of c dot product with c prime, which is tangent to our curve c, dt. And then if we just divide this tangent by its magnitude and multiply by the magnitude, and here we will have unit tangent, and I call this unit tangent t. And then we are computing this dot product, so here is the dot product, and it will give us a tangential component of our vector field f along c, and then we can, and it will be a scalar. So then we will have scalar, and here we just have regular integrals. So the point of this was just to remind you how to compute line integrals, how to reduce them to usual integral that we use in Calc 1. And so now let's recall how to compute integrals of scalar functions, but over surfaces. Right? Suppose we have a surface S. Here notations are as before. So Fs is a parameterized surface, and D is this domain in R2. And so if we want to compute this integral, then we use our parameterization. Phi is our parameterization. We can plug everything in, and then here, if we want to write everything in terms of u and v, it will be magnitude of the cross product of tangent vectors tu and tv, du tv. And if we compute the the magnitude of this vector, then we will get this expression. And here I just explain notations how to compute each of the elements, explained using the first one. This is just determinant, and this will give us area element. So if we want to compute area of some surface S, we just need to compute such integral. So now let's recall what are surface integrals of vector fields. So here we suppose that F is vector field and S is an oriented parametrized surface, and all notations are as before. So S is the image of d phi of d, and the meaning of physical meaning of this integral is a flux of S across the surface S. So you can think of an example. So if F is a velocity vector field, so suppose we have a fluid somewhere, moving fluid, and F is this velocity vector field, then, and if we assume or imagine a surface somewhere inserted into the fluid flow, then flux is a net quantity of the fluid to flow across the surface per unit time. So it's a rate of our flow. So this is the physical meaning of the flux, and we will be dealing with fluxes of different nature as well. So and here I started talking about how to we can compute this integral, and if we divide and multiply by the magnitude of this vector, right? So I continue here. So then, of course, integral will not change, but here we will have a unit vector, and remember that cross product of these two vectors gives us a normal to the surface, the point. So if we divide by its magnitude, it will be unit normal. And then if we recall what we discussed previously in this video, so this would be area element, and this is unit normal. So then we have F, dot product of F with this unit normal. It will give us normal component of our vector field. So it is a scalar. So now we are dealing with integration of scalar functions over the surface, which we discussed earlier. So this is something that we'll be using in derivations. The notion of flux is important. And I also would like to recall important theorems of vector calculus. The main of them is Stokes theorem, or Stokes formula, and in a separate lecture I will discuss generalization of this formula. But here let's think of S to be an oriented parametrized surface, and ds be its oriented boundary. So then this is Stokes formula, so we can see how we can change integration if we want to, from integration over the surface to integration along the boundary. And here we assume that F is a C1 vector field with components F1, F2, F3. Here I just remind you that this cross product of del operator F is a curl, and it can be computed at this determinant. So this is the Stokes formula. Its simpler version is Green's formula. Simpler, I mean, if now D is just a flat two-dimensional domain, and this DD is positively oriented boundary, then we have the following formula. So here we assume that functions P1 and P2 are functions of xy, and the C1 a function, then the following formula holds. This is Green's formula, and we can rewrite this formula in vector form if we introduce the notation vector P has components P1 and P2. Then we can rewrite left hand side in this form and right hand side in the form of kind of two-dimensional curl. So here I explain what I mean. So if we write regular curl, but we don't have the third component, so it's 0, and then when we will be just computing this determinant, we will see that coefficients of I and j is 0, so we have only one non-zero component, so it will be coefficient of vector k. So this was Green's formula, and now another important formula is Gauss divergence theorem. So now we are talking about three-dimensional region or domain in R3, right? And here we also can switch integration from integral over this volume to the integral over the surface, which is the boundary of this domain W. And here, so this integral on the left hand side can be, if we use this computation similar to those, we can see that it's just can be written as the integral of normal component of our vector field, normal component to the boundary. And it should be clear how to compute this integral if we need to. And in the right hand side, here we have dot product of del operator and F. So, and this gives us divergence of vector F, which is computed as follows. So here was the quick reminder from vector analysis. Thank you.